In this video, I'll be working through last year's Grade 10 Term 1 Math Investigation, which focused on trigonometry. Since this year's investigation is also based on trigonometry, and you haven't been formally taught the section yet, this will give you a better idea of what to expect. Typically, a math investigation requires you to research and explore the topic on your own before applying it. So my goal is to give you a quick guide through a similar investigation to help you approach yours with confidence and clarity. If we have a look at the cover page of this investigation, we notice that it was for a total of 50 marks and it was written within 60 minutes. Here's a breakdown of the questions. We have questions 1 to 5. There's the corresponding mark allocation to give you the total of 50 marks. In this video, I'll be working through question 1. So there is a bit of information given before we get to question 1, and it says complete the following. In a right-angled triangle, we can name the sides of the triangle according to the position of the angle and the right angle. So to understand trigonometry, let's first discuss the basics of trigonometry, then we can go ahead with reading what we have here. Basic trigonometry in grade 10 deals with a right-angled triangle. Let's call this triangle ABC. Now we are aware that this symbol that we see here is how we represent angles that are 90 degrees. And let's choose to represent another angle. I'm going to go with angle B, and I'm going to call angle B theta. Now, in terms of theta, we can label all three sides of the triangle with reference to theta. So the side of the triangle that lies opposite theta would be known as opposite. So I've labeled it opposite. The side that lies next to theta would be known as adjacent. So we know that in maths, the word adjacent we hear quite often, and it means next to. So this side AB of the triangle is next to theta, so we call it the adjacent side. And what we're left with now is CB, or we can say BC, that is opposite the 90 degrees. This is something you already know. The side that lies opposite the 90 degrees in a right-angled triangle is called the hypotenuse. So now we have all three sides of our triangle labeled. So in terms of theta, the side that lies opposite theta is called opposite. The side that lies next to theta is called adjacent. And the side that lies opposite the hypotenuse, or opposite the 90 degrees, is called the hypotenuse. Now from this, we get three important trig ratios. The first trig ratio is known as sine. And why it's called a trig ratio? Ratio in maths means fraction. So there is a fraction that represents sine. In terms of theta, sine is equal to opposite over hypotenuse. So I'm going to write that as O over H to represent opposite over hypotenuse. So in fact, on our triangle, opposite is represented by AC and hypotenuse is represented by BC. But just to remember this trig ratio, we'll remember it as opposite over hypotenuse. Because remember, they can label the triangle differently. They can position the letters differently. So it's important that no matter what labeling you have on your triangle, you understand the trig ratios and how to make use of them. The next trig ratio is known as cos. So cos in terms of theta is adjacent over hypotenuse. So I'm just going to write that as A over H. So notice the difference. Sine is opposite over hypotenuse. Cos is adjacent over hypotenuse. And there is one more. The third trig ratio is called tan. In terms of theta, tan is always opposite over adjacent. So sine is opposite over hypotenuse, cos adjacent over hypotenuse, and tan opposite over adjacent. So coming back to the information that was on the investigation, we were given two diagrams. And on the first diagram, we've got the angle represented as beta. So this is a Greek letter called beta. And in terms of beta, the side that lies directly opposite is called the opposite side. The side that lies next to beta is called the adjacent side, and the side that lies opposite the 90 degrees is called the hypotenuse. Or, represented differently, and now this is more of what I've shown you, where we're now using the angle at the bottom and we're calling it theta. So the side opposite theta is called the opposite side. The side next to theta is called the adjacent side. And the side opposite the 90 degrees is called the hypotenuse. So they say investigate the different ratios of all the sides in similar triangles. So similar triangles is something that you are familiar with from last year. We know that when triangles are similar to each other, they are in proportion, meaning that they have all the same angles, but it could either be scaled up or scaled down. The four triangles below are given from smallest to biggest. The corresponding sides opposite the common angle theta is shown on the sketch as parallel lines. The angles which are equal are shown as stars. Use the following sketch to answer the questions in this investigation. So our questions from question 1 is based on this diagram. At the moment, they are testing you on your knowledge of similar triangles. Let's now look at question 1. What they've done is they have given us lengths of the lines. So they've assigned a different length to each segment. First off, we've got AB equal to 4.9 centimeters, AD is equal to 8.5, AF 11.8, AH 13.9. And then in the next row we have AC, AE, AG, and AJ. And thereafter we have all the vertical lines, so CB, ED, GF, and JH. So we have lengths for every line segment on this diagram. 1.1 says, complete the similar triangles by writing the letters of the triangles in the correct order. So here we have triangle ABC is similar to, and you guys remember from last year that the similar sign are these three vertical lines. So if we go back up to our diagram, this is triangle ABC. And we want to know what it is similar to. So we're looking for other triangles that are of the same shape and have the exact same angles as ABC. So the next triangle, or actually the first triangle that would be similar to triangle ABC, is triangle ADE. And bear in mind, I am following the same order of the letters where they called this triangle ABC. The next one would be called ADE. How do we know that they are similar? We notice that all of their corresponding angles are equal. Here, angle B and angle D are both 90 degrees. Angle C and angle E, they're equal because they're represented with a star. And angle A for both triangles are the same because it is a common angle. It lies in both triangles. So the first answer we have, ABC is similar to ADE. And now we need two more triangles. Now the next similar triangle that we should have should be AFG. So AFG is similar to ABC because all of their matching angles are equal. So here we have A, F, G. And now we need one last triangle. So the last triangle that is similar to ABC would be AHJ. AHJ is similar. 1.2 says, why are the four triangles similar to each other? So I spoke about this not too long ago, and I said that when triangles are similar to each other, all of their corresponding angles are equal. So we're allowed to say that corresponding angles are equal. We're also allowed to say that, well, another word for triangles where corresponding angles are equal is equiangular. So we can say that all the triangles are equiangular, or we can say corresponding angles are equal. Then 1.3 says, why is it important to write the letters in the correct order when it comes to similarity? So the reason why we do this is because when we write them in the correct order, it allows us to see which sides correspond, or which sides are similar to each other, and which angles correspond to each other. What I mean by that is, when we had the first two triangles, ABC and then ADE, it showed us that ABC and ADE, the line AB and AD were similar to each other. The line BC and DE were similar, and AC and AE were similar. So when we write it in the correct order, it's a lot easier for us to identify the sides that are in proportion with each other, so the sides that are similar. Okay, so that allows us to determine the corresponding sides and angles. Okay, we will now look at question 2. So question 2 says, 2.1, complete the table by writing down the correct sides of the triangles ADE, AFG, and AH. Firstly, in this table, they have given you the answers for triangle ABC. And for ABC, they have the opposite side as CB, the adjacent side as AB, and the hypotenuse as AC. So what we should actually do is fill that in on the diagram that was provided. So the opposite side was CB. Let's go up to that triangle. Okay, the opposite side, so in terms of theta, right? That's how it was given. The opposite side was CB, and I'm just going to write down an O for that. The adjacent side was given as AB, and the hypotenuse was given as AC. Now that is correct. That makes perfect sense regarding this angle theta. Remember, the side opposite theta would be the opposite side, the side next to theta would be the adjacent side, and the side opposite the 90 degrees would be the hypotenuse. Now they expect you to complete the table for the remaining three triangles. So in terms of those triangles, we need to find their opposite, adjacent, and hypotenuse. So the first triangle we're looking at is ADE. So here we have triangle ADE. This is it. And for this triangle specifically, here we have theta. In terms of theta, the opposite side should be DE. This would be the opposite side. The adjacent side, so the side next to theta, would be AD. So this would be adjacent, AD. And the hypotenuse for this triangle, which is opposite the 90 degrees, would be AE. Sorry. That's supposed to be H. Okay, that's the hypotenuse. So let's just remember, the opposite side is DE, the adjacent side is AD, and the hypotenuse is AE. So there we have it. I filled it in. The next triangle we're looking at is AFG. So here I've outlined triangle AFG. There's theta in this corner. Remember, the side opposite theta would be called the opposite side, which is FG in this case. The side next to theta would be the adjacent, which is the bottom part of the triangle. That's AF. So that's going to be the adjacent. And the hypotenuse is opposite the 90 degrees. That is AG. So the opposite side here was FG, the adjacent side is AF, and the hypotenuse is AG. Let's fill that in on the table. Now the next triangle we're looking for is AHJ. Let's refer to the diagram. So AHJ is the entire, it's the whole big triangle. And here we have theta in the same corner, so the side opposite that would be HJ. The side adjacent would be AH, it's this bottom part. And the hypotenuse would be opposite the 90, there's our 90 degrees. So opposite that is this entire slanted line, that is AJ. That would be our hypotenuse. Let's fill that in on the diagram. Okay, so filling that in on the table given, this is what we have. We can now go on to 2.2. 2.2 says complete the table below. So in terms of our answers that we had from 2.1, they now want the lengths of each side. For example, here we had CB. So since we had CB here, in 2.2, we need the length of CB. Basically, we're going to fill in the corresponding lengths, and it's actually quite simple since the lengths were given to us in question 1. There's all of the lengths. All we have to do is find it and fill it in. So the first value we had in 2.1, let's actually go vertically, right? So we have CB. So we're going to fill in CB here, and the corresponding value for CB, if we just scroll up, is 2.3 centimeters. So there we have it, 2.3. The next value we need is AB and then AC. Here's information from question 1. AB is 4.9, AC is 5.4. Now, these are the rest of the sides that you need. I'm going to scroll up to the information given under question 1 where we have the lengths, and I'm going to give you a bit of time to try it out on your own to fill in the table. You can pause the video and continue, and I will fill in all of the values and then proceed. So this is my completed table for 2.2. So we're now going on to 2.3. It says complete the ratios by using the previous two tables and use your calculator to round it off to 1 decimal place. So they are expecting a final answer from us here, and we would have to calculate and give it as 1 decimal place. Now firstly, we're working with triangle ABC, and they want us to get the opposite side over the hypotenuse. So let's scroll back up to where we had these values. For ABC, and we're making use of table 2.2, the opposite side was 2.3, the hypotenuse was 5.4. Let's fill that in. So there we have it, 2.3 over 5.4. Now let's put this on the calculator and get it as 1 decimal place. As 1 decimal place, your answer will be 0.4. Then, the next fraction we need is adjacent over hypotenuse. If we scroll back up to 2.2, adjacent is 4.9, hypotenuse is 5.4. So here we have 4.9 divided by 5.4. Let's get our answer on the calculator to 1 decimal place. And our final answer there is 0.9. The next ratio we need is opposite over adjacent. Opposite is 2.3, adjacent is 4.9. And getting the answer as 1 decimal place, that is 0.5. So this is basically what they want you to do for the remaining 3 triangles. You're going to refer to the table in 2.2. You're going to fill in the values and then get your answer on the calculator to 2 decimal places. You can pause the video and try it out. Okay, so this is what your completed table should look like. These are your values. Now going on to 2.4. So 2.4 says, check the values of the ratios for every triangle that we calculated previously. So based on the same table that we had. 2.4 says, did the value of the ratio of the opposite side over the hypotenuse change or stayed the same for all the different triangles? Now, if we refer to the table and we go to the part that's opposite side over hypotenuse, we notice that all the values were in fact the same since they all were 0.4. So answer is the same. For 2.4.2, it says, did the value of the ratio of the adjacent side over the hypotenuse change or stay the same for all the different triangles? So let's refer to that table. And here we notice adjacent side over hypotenuse, all of the answers were 0.9, so they stayed the same. 2.4.3 says, did the value of the ratio of the opposite side over adjacent sides change or stayed the same for all the different triangles? Let's just refer to that table to verify. There's opposite over adjacent, and we notice all of our answers were 0.5, so they all were the same. So your answer there is the same. We're now on to question 3. 3.1 says, if the size of the angle theta in the sketch on page 3 is theta is equal to 25 degrees. What that means is the diagram that was initially given to us, where we had theta, that is 25 degrees. So it's this initial diagram that we had. Theta here is 25 degrees, meaning that all of the information that we had afterward, where we calculated the ratios here for 2.3, the angle that we used was 25 degrees, but it's just that at the time we were not given the angle yet. So 3.2 says, use your calculator to determine the value of the following to one decimal place. The first thing they want is sine 25. Now you're going to do this on your calculator. So you're going to press, you have a button for sine, you're going to press sine. It automatically opens up a bracket. In that bracket, you will put 25 and make sure that you close the bracket, then press equal to. They want the answer to one decimal place. This gives us 0.4. We now need to get cos 25. So cos 25 to one decimal place is 0.9. And then tan 25 to one decimal place, that is actually 0.46, but when we round off to one decimal place, it becomes 0.5. 3.3 now says, compare your answers in table 3.2 and 2.3. Choose only one option by marking the correct column on the right hand side by X. Okay, so firstly, it says sine 25 had the same answer in 2.3 and 3.2 as. So let's first go back to those questions, 2.3 and 3.2, and let's see what sine 25 was. So in 3.2, sine 25 was 0.4. And when we go up to 2.3, which is this table, 0.4 was the same thing as opposite over hypotenuse, meaning that we are going to put an X next to opposite over hypotenuse to indicate that is what sine 25 matched. Then cos 25 had the same answer. Let's go back up to those tables. Here for 3.2, cos 25 was 0.9. And then for 2.3, 0.9 corresponded to adjacent over hypotenuse. So here we are going to put an X next to adjacent side over hypotenuse. Now tan 25 had the same answer as. Let's go back to those questions. Tan 25 here corresponded to 0.5, and in table 2.3 it matched up with opposite over adjacent. So here we're going to put an X next to opposite over adjacent. 3.4 says, do you think that the previous ratios will always be the same for the same angle sizes, although the triangles may differ in size? Basically what they're asking you is, we've had similar triangles. Will it always be the case when we have similar triangles that the trig ratios will have the same answers? Like when we looked at table 2.3, we noticed that they all had the same opposite over hypotenuse. They all had the same adjacent over hypotenuse. They all had the same opposite over adjacent. So that's what they're asking you. When you have the case where the angles are the same in all of your triangles, meaning that they're similar, will the ratios always be the same? So the answer should be yes. And provided that it's a right angle triangle, it would work that way. And provided that the triangles are equiangular, yes, it would work that way. So as our answer, we can say yes. So here's your two reasons. Yes, it must be a right angle triangle and the triangles must be equiangular. Or you could say that there should be another angle that's equal. But that comes down to it being equiangular anyway. We're now on to question 4. It says, in the following exercise, the right angle triangle XYZ is given. And not very clear, but you notice that angle X here is 35.3 degrees. Then it says, 4.1, in the given triangle there are 3 sides. Write down which one of the sides XY, YZ, or XZ will be the. So which one would be the opposite side of 35.3? Now it would help us if we can actually label this triangle first before we start. Doing that, in terms of 35.3 degrees, the side opposite would be our opposite side. The side next to that would be adjacent, and this would be our 90 degrees. Even though it's not given to us, we can clearly see that these two sides are perpendicular, and the side opposite the 90 degrees would be the hypotenuse. Based on that, we can easily fill in the side. So opposite 35.3 is YZ or ZY, but they've called it YZ, so let's write it like that. The adjacent side is XY, and the hypotenuse is XZ. .2 says, if YZ is the wanted side and XZ is the given side, which ratio? So here they've given you opposite over hypotenuse, that's sine, adjacent over hypotenuse, that's cos, opposite over adjacent, that's tan. Which ratio will you use? Now seeing that we want YZ and we have XZ, XZ is given, YZ is opposite and XZ is hypotenuse. Since we have opposite and hypotenuse is sine. So the ratio that we have to use, writing it how they have it, would be O over H is equal to sine of 35.3 degrees. And now for 4.3, it seems like they actually want us to do this calculation. So we need to determine YZ. And writing down what we had, okay? YZ was the opposite side. So we've got YZ over XZ is equal to sine of 35.5 degrees. All I've done is I've replaced opposite and hypotenuse with what the sides were. Now they've given you a value. they said that xz, which is the one in the denominator, is 32 centimeters. So we're going to have xy over 32 is equal to sine 35.5. And what you need to understand here is that you are solving for xy. That is your unknown. So to get that alone, we're going to take this 32 and we're going to multiply across. But please bear in mind that when you multiply across, it goes in front of sine. So what that ends up looking like is xy is equal to 32 sine 35.5. And when you put that in on your calculator, you would type it in as you have it. So you will punch in 32, press sine. Sine automatically opens up a bracket. So in your bracket, you're going to fill in 35.5. Make sure you close the bracket. And okay, a small thing that I noticed here, it was actually 35.3. Okay, so in the previous steps, I just corrected that. We can see here it's 35.3. So substituting all of this into our calculator, therefore, we get xy as 18.49. And bear in mind that 18.49 is a length. Since they were using centimeters, we're going to have this answer in centimeters as well. So that is the value for xy. We are now on to the last question of this investigation, which is question 5. So the writing isn't very clear, but what we have here is a horizontal line. It looks like there is a boy looking up at a tree, and his line of sight here is creating a horizontal line. He is looking up at the tree. So from this horizontal line, there's a certain angle that he's looking up at that is known as the angle of elevation. And the direction in which he's looking, that is known as the line of sight. So what they've done is they've taken these lines together with the angle and they've drawn a right angle triangle for you, where we can see that the angle is 66 degrees. The horizontal line is 50 meters. And so we definitely know that this is where the hypotenuse, this is where the 90 degrees lies. So the hypotenuse is opposite that. The hypotenuse would be RH. Now the information says, or the question says, Ryan R. So R represents Ryan, is looking up at the cliff of a mountain. He is 50 meters from B, the bottom of the mountain, and the angle of elevation from where he stands is 60 degrees. Determine the perpendicular height of the mountain. Use question 4 as a guideline, and obviously the diagram is not drawn to scale. So this is what we're going to do. Ideally, it would be best when you have a question like this, label the sides of the triangle with regards to the angle that you are given. Here we have 66 degrees. The side opposite the 66 degrees is BH. So I'm going to label that O. The side next to the 66 degrees, which is this 50 centimeters, RB, that is the adjacent side. And the side opposite the 90 degrees is the hypotenuse. I'm going to call that H, which is RH. Now that we know what we're dealing with, we need to figure out exactly what they're asking us to calculate. They want the vertical height of the mountain. The vertical height is represented by BH. So what we're solving for is the opposite side. Now, when you're trying to solve for a side in a right angle triangle, you can either use sine, cos, or tan. But obviously, you need to use the formula that you have the most information for. In this case, what we have information for is the adjacent side. So we need the opposite side, but we have the adjacent side. So we need to use a trig ratio that actually has opposite and adjacent in it. That is going to be tan. Tan is opposite over adjacent. So let's start off by writing down our formula that we're going to use. This is the formula that we're using, right? Tan, which is opposite over adjacent. But we need to replace the opposite and the adjacent with the actual letters. So opposite here is represented by BH. Adjacent is represented by RB. So one thing I want you to take note of is that a trig ratio has to have an angle next to it. So on the left hand side, it is actually tan 66 degrees, since that was the angle on the triangle. Opposite is BH and the bottom is RB. In the next step, let's replace RB with what it's equal to. So we have tan 66 is equal to BH and RB was 50 meters. Since we want to solve for BH and we want to get rid of 50 in the denominator, we're going to take that 50 and we're going to multiply across. When it multiplies across, it goes in front of tan. So this becomes 50 tan 66 is equal to BH, which you're just going to put on your calculator to get the answer. So it's 50 tan 66. And the answer that I have for BH is 112.30. This is measured in meters, so that is going to be your final answer, 112.30 meters. That is the end of this investigation.